Okay, here we have a finite group, right? And two elements of the group, x and y. And well, it says R, but it should say Q, because it's this Q we're talking about here. Q is an integer, an arbitrary integer here. So we have to prove that, well, this some properties of the order. The order of an element is the order of the inverse of the element. The order of an element x is the same as the order of this product of elements, right? Where y is an arbitrary other element of G. The order of x times y and of type y times x is the same. And if x to some power q is equal to the identity, then the order of x is a divisor of q, right? So we need to prove this property. So let's begin with the first, okay? So we have this first property. And let's say that the order of x is k, right? Just to simplify notation, right? Now we're going to do the following. We take the product of y, some arbitrary y times x minus k, right? Which is the k power, by the way, x minus k is just the k power of x minus 1, right? Okay. So we take this in and we calculate what the inverse is, right? Well, the inverse of this is, of course, the product of the inverses in reverse. So the inverse of this is just xk, and then you have times the inverse of y. Okay, xk by definition, this is the order. This is just e, so this is just y minus 1. So we have two elements, this and this, whose inverses are the same. Therefore, the elements themselves are the same. So y times x negative k is equal to 1. And this is exactly the property of the neutral element. So that means that x to negative k has to be the neutral element, right? Okay, what this is saying is that k is smaller than or equal to, sorry, no, not that. That the order of x minus 1 is smaller than or equal to k, right? So because if we raise it to k, then we get that this is the identity. But it could happen that even, well, the order must be the smallest such k. So this is 1k for which this is true, but we're not sure whether this is the smallest. So the order should be some number at most k, right? A number which is k or smaller than k, right? Let's try to prove the opposite, right? So remember, k is just the order of x. So what we're doing is, what we have just proven is this. However, x is equal to the inverse of x minus 1. So if we apply this to x minus 1, what we have is that the order of x minus 1 is smaller than or equal to the order of x minus 1, right? So here, this is valid for any x, right? This is valid for any x. So in particular, if we take x minus 1, this is also valid, right? But this is just x, so this is just the order of x. So what we have is that the order of x is smaller than or equal to the order of x minus 1. So if both inequalities are true, then the order of x minus 1 has to be equal to the order of x, right? So here's the first property. Now the second property that we need to prove is this one. And we're going to use this property, which is easy to prove. If we have this composition, right, and we multiply it by this other one, y times x to m times y minus 1. N and m are arbitrary integers, right? Arbitrary integers. Then, if we make, we apply the associative property, this is equal to this times y minus 1 times y times x to the m times y minus 1. And of course, this is equal to the identity. So what we have here is the product of these two powers. So we add the powers, and we just have y times x n plus m times y minus 1. Okay, if you will multiply these constructions with two different powers, the result is the same construction with the sum of the powers. Okay, then it's easy to see that by repeated application of this property, if we have this construction, right, with x here, and we raise it to the kth power, okay, then the result is just y times x to k times y minus 1. Okay, because we're just multiplying these together k times, and every pair of them can be applied. We can apply this property to every pair of these products, and the powers are adding, and we have k of them, so at the end we have xk here. All right, now if k is the order of x, and this one here is the identity, and what we have here is just y times y minus 1, which is also the identity. So this element to the power k is equal to the identity, which proves that proves that the order of y times x times y minus 1 is smaller than or equal to the order of x, right? It's the same story, right? We know that k is a power such that this element to this power gives you the identity, but we need to prove that this is the smallest power, right? So we're sure about is that the power for which this happens has to be k or smaller, right? And this is what it is written here. This is k, remember, this is k, okay? Fine. Now we're going to prove the opposite inequality by writing x in this specific way. We write this as this composition, which is true if we take z equal to y minus 1. Right? If we take y minus 1, then we have y minus 1 times y is just identity, and here we have y minus 1 minus 1, which is y, and y minus 1 times y is the identity. So the identity here is just x. So this is a bit baroque way of writing x, but this is going to be useful for our purposes. Because look at this inequality here, right? Now this construction is playing the role of x. So we can apply this here and say the order of this whole construction, which is just x, is smaller than or equal to the order of this element, which is y times x times y minus 1. And that is the reverse inequality of this one. So the conclusion is the order of x is equal to the order of y times x times y minus 1. All right? Okay. Now, the next property is we have to prove that the order of xy is equal to the order of yx. Okay? Right. Let's see. We're going to use, we're proving that. Well, let me just erase this to make it more clear. Okay? So, okay. Right, so let's go back here, okay? And now we need to prove C. And we're going to prove C as a consequence of this result here. And the way we're going to do this is the following. Take y times x, okay? And we're going to write this as y times x times y times y minus 1. Actually, we can prove it. We can put it like this. Okay. This is just the identity. So this is just multiplying by the identity on the right. So that's fine. But now we can group this in a different way. We can group it like this. All right. what this is telling us is that this element, whatever it is, can be expressed as this times this times this, right? Which has exactly the same structure. So we know that the order of this, which is this one, so the order of this thing here, y times x times y minus 1, this is just the order of y times x. What this property says is that it's equal to the order of this element here. So that's the order of x times y. And now we have the result that we wanted. Okay. And finally, we need to prove this. All right. So again, let me just call k the order of x. All right. Just for simplicity. What we're going to say is, well, if we divide q by k, we will have an m multiplied by k and an r, where r is in this range. Okay. Sorry, smaller than k. Right. R is in this range. Okay. So x to q is equal to x to n plus k, n times k, sorry, plus r, and that is x to the m to the k, the other way around, sorry, x to the k to the m. Okay, remember when you do this is you just multiply the two powers, so mk times x to r. All right. Okay. Now x to the k, remember is the order of x, so this is equal to e, and e to m is just e, the identity, and the identity multiplied by this is just this, right? And x to the k is equal to the identity, therefore this is equal to the identity, right? So we're just transforming this expression, which we know is the identity, we are just transforming it, and then we find out that this is equal to this other one. But r is smaller than k, right? And k is the order, and k is therefore by definition the smallest non-zero integer for which this is true, right? X to the k is equal to e. K is the smallest non-zero integer for which this is true, and r is a smaller integer, so the only possibility in this range is that r is equal to 0. So that means that r is equal to 0. And if r is equal to 0, then you go here, you get that q is equal to m times k, which means that k divides q, and that is exactly what we wanted to prove.